Good afternoon. It's my great pleasure to welcome all of you here to the 2013 Nora and Edward L. Ryerson lecture. This is an annual event, as I believe most of you know, and it's a very special event for the University of Chicago and for the faculty of the University of Chicago. This is an event that happens only once, and it's not just the Ryerson lecture that happens only once every year. But the process that leads up to the selection of this speaker happens only once every year. And that is that a faculty committee, based on nominations from our colleagues all over the university, make a decision about the one person that they want to hear speak about their work. So this is something that reflects inevitably the highest aspirations of the University of Chicago. And when you look at the history of speakers, this is now the 40th year of the Ryerson Lecture. When you look at the speakers, you see veritably a piece of the intellectual history and a reflection of the enormous dynamism of the faculty of the University of Chicago over these 4 decades. This lecture series was made possible by a bequest from a former chair of the board of the university board, Edward L. Ryerson. And we've had the benefit of members of that family being here with us during all this time. And George Ranney is here, other members of the family. George is a trustee emeritus, trustee for many, many years. And I want to thank the Ryerson family and its multiple generations, and particularly thank George for his years of leadership connected to the university. Now, it's really a great privilege to be able to introduce this year's Ryerson lecturer, Michael Turner. And I just want to mention that the very first Ryerson lecturer was John Hope Franklin. The second lecturer was Chandrasekhar. And there have been others in between, some of whom I see in this room, who have a somewhat similar spirit. But I do want to say that Michael is here not only as an extraordinary scientist, but as part of what has been an extraordinary intellectual tradition at the University of Chicago. I think most of you know that Michael has been instrumental in the development of the entire field of particle astrophysics, which in one way or another I'm sure we will hear about today. And he, one of the aspects of this is that his work is also been very important in demonstrating the relevance of quantum effects for the large-scale structure of the cosmos, which is interesting to think about. And I'm not sure exactly what he's going to say, but if he doesn't say anything about that, you'll have lots of time to ask him about it afterwards. Michael's has an extraordinary long CV, which he asked me not to read, so I wouldn't take away from his time because he wants his time to talk to you about physics. I do just want to say he's the Bruce and Diana Rauner Distinguished Service Professor. He's the director of the Kavli Institute for Cosmological Physics, which he helped to establish. He has a long list of awards from Physics Society, astronomical societies, which I will not read. But I do want to say that Michael, in addition to his science and his work at the university, has been an extremely important figure in terms of the national structure of physics and astrophysics. He was chief scientist at Argonne National Laboratory. He's been assistant director for the mathematical and physical sciences division at the National Science Foundation, which is a very important position for quite a number of people in this room. He was chair of the Department of Astronomy and Astrophysics here, chairman of the board of the Aspen Center for Physics, and on the list goes, and he's currently the president of the American Physical Society. So it's a great pleasure for me to introduce a person who has surely demonstrated through his extraordinary work over the years, the very highest aspirations of the university. Michael Turner.
Thank you very much. Great. When I got the call from Bob Zimmer, I was extremely happy and honored, and I was glowing for almost a week. And then I went and looked at the web page to look at the previous speakers, and then I started getting really, really nervous and, excuse me, paralyzed even. And then I was doing extremely well until today, when I looked and it said the speaker was supposed to reflect. And, well, we don't do that. I don't reflect. But I did decide to wear a blue suit rather than a black suit because I think a blue suit reflects more than a black suit. And also, the other thing about it is physicists, and especially astrophysicists, are capable of speaking even when they have nothing to say. So, but I do think I have something to say. I don't want to. So I thought I would begin with how I came to California, how I came to Illinois. I came from California, so that was me. And this was, when I came to Chicago, this was only the second or third time I'd ever been out of California. I came to Chicago and asked people, I don't understand how it snows so much here, because in California it only snows in the mountains, and I thought that Illinois didn't have mountains. Anyway. And Jim Cronin, I think more than once, I see him sitting here, has said he had California written all over him. Is that true, Jim?
It's true.
And, but, you know, if you remember so that was, I came as a Fermi Fellow. I joined the faculty 2 years later. I survived the famous blizzard of '79. Do people remember that blizzard? And I think that established that I had some kind of, you know, metal in me. And, but really the reason that I survived here is this is a really, really great place. And I had a great mentor and many, many supporters. My mentor was David Schramm, who eventually became vice president for research. And I like this picture of him very much. This is one taken just about the time he came. And David, I spent my first night in Hyde Park in his house, and he loaned me, as some of you who know David, he loaned me Ian Lerch's car to drive around Chicago. And he introduced me to my wife. So he was a, you know, full-service mentor. And so David will figure in this story, but it wasn't just having a mentor. It's having supporters. And I apologize, I only have, you know, 4 or 5 pictures up here, but this could have gone on forever. Everyone at Chicago wants to see a young postdoc or faculty member succeed. And so I put the 2 directors of the Enrico Fermi Institute up here, John Simpson and Peter Meyer, that I worked with. Gene Parker, I didn't know how important he was. And I just knew him as someone who was willing to talk to me and listen to me. And these 2 gentlemen, now both Nobel Prize winners, called me up to make appointments to come see me. And the list could just keep going. I see the audience and so many people. This is a great university. And your only limitations here, as far as I'm concerned, are your dreams. And so anyway, that's part of this story. I want to say that at the beginning, and hopefully I'll remember to say it again at the end. So let me define cosmology for you. It's the scientific study of the origin and evolution of the universe. And I want to tell you something. The universe is really, really big. And so if anyone ever asks you a question about the universe, just say billions, and you're probably right. And in order to make progress towards understanding the universe, you need big ideas and you need powerful instruments. And does that sound like a Chicago subject, one that would do well here? Okay. So around the time the University of Chicago was being founded, and I actually know what year it was founded, but I'm using round numbers here. So around 1900, this is what the known universe looked like. So it was the Milky Way galaxy, Everybody knows the Milky Way. Well, in Chicago, you can't quite see it during the summer. But so there was one galaxy. There were a few million stars that could be seen with the most powerful telescopes. So I'll give you the big numbers later. It was an unchanging cosmos, and there was one little loose thread. And the loose thread, I paint with a very big brush for my colleagues, so I know there were other loose threads, but on the big picture there was one loose thread, which was the nebulae. So these were fuzzy patches on the sky that had been cataloged starting in the 18th century by Messier and Herschel, and so squint. I'd like you to squint, because most of them you can now say, well, that's a galaxy and that's a galaxy. But the telescopes weren't so good then. And so the question is, what are these? Are these just clouds in our galaxy? Or, as Immanuel Kant had speculated, are these island universes, other galaxies? That was the big question at the time. So let me now turn to the University of Chicago and two men with very big visions. And of course, everybody knows Harper. And when I was preparing this lecture, this was a quote I had never seen before. And it's a wonderful quote. We've heard all these stories about Rockefeller praying with Harper and money. But you know, I'll read it for those who can't see it. I gave him an unlimited budget, and he exceeded it. And that is the spirit of the University of Chicago. And you know, so he was Rockefeller's nemesis, but his nemesis was George Ellery Hale, pictured here with his later benefactor, Andrew Carnegie. And Hale was the founding chair of the Department of Astronomy and Astrophysics, and he insisted that Astrophysics be in the title. He was the founding director of Yerkes Observatory, and he's the person who convinced Charles Yerkes to give the money for the observatory. He's a man who thought really, really big. And so Yerkes Observatory, if you haven't been up there, it's what an observatory is supposed to look like. So beautiful lawns. This is the dome that has the telescope that Hale convinced Yerkes to donate the money for. So what I like to tell people is it's a real telescope. You know which end to look out of. So you just stand right here and look. And it's a 40-inch telescope, and it's a refractor, but the English for that is it's a lens. It's a lens-type telescope. And it was the largest telescope in the world when it was completed. I think it was 1897. It is still the largest refractor telescope. And another way to put that is it was the last refractor telescope built. It made Chicago, well, I said the center of astronomy, maybe one of the centers. And here's a photograph from May 6, 1921. And if I point the pointer at this gentleman, so Albert Einstein, on one of his first trips to the US, visited Yerkes Observatory. So it was really, really important. It was an important observatory, and a lot of fantastic work was done there. But I want to restrict myself to cosmology. And so Hale, after getting this observatory going that became a world center and this and that, Hale to Harper. The future of astronomy is big reflectors in the mountains of California. Harper to Hale, I wish you well. And we'll come back to that at the very end. Let me just talk about reflecting telescopes, because in order to build bigger telescopes, you had to do it differently. And Hale, and fortunately he had a man named Ritchie working at Yerkes Observatory, George Willis Ritchie. And this is the prototype for all modern telescopes built in Wisconsin at Yerkes Observatory. So it's a 24-inch reflector, so that means it's a piece of glass that's aluminized. And so you can actually support it. The trouble with a lens is it starts to sag and so on and so forth. And so this is the prototype of all modern telescopes built by George Ritchie at Yerkes Observatory. Is this a wonderful picture, or is this a wonderful picture? So this is a Yerkes expedition to an exotic spot on Earth to see a solar eclipse. And that exotic spot was Wadsboro, North Carolina. And it kind of looks like they maybe were getting some moonshine there or something. And there is Ritchie. And for the discerning eye, you can see Hale there. And so they're there to see the solar eclipse of 1900. And so Hale went to California. And the first thing he did was to build a 60-inch telescope with the help of Ritchie at Mount Wilson. So we're going to do some counting here. That's the second time he built the world's largest telescope, except now it's at Mount Wilson in California, and his benefactor was Andrew Carnegie. And so that's the 60-inch telescope. This is Mount Wilson. And the telescope that Hubble used that made the discoveries I'm about to talk about next, the fact that the universe is expanding and that there are billions of galaxies, involved the 100-inch telescope, which he built after that, just big enough for the job. And so in these reflecting telescopes, here's where the mirror is. And the light comes in, and the light's reflected off the mirror. And this is called the prime focus observer's cage. And you can actually go, in the olden days, the observer would sit up there with paddles and expose a photographic plate, and it was very romantic. Actually, I'm a theorist, and so I've never done that. I'm looking at Lou Hobbs here, and I think I got it right. This telescope was, of course, named after the very civic-minded group of ladies in Pasadena. No, it was named after John Hooker. Okay, and then Hale went on to build for the fourth time the world's largest telescope, a 200-inch reflector, but he needed a new site, Mount Palomar. And this telescope, you really have to study this picture to see where the telescope is. There's the mirror, and this is just structural support. It's called a polar mount. It supports the telescope. And so for the fourth time, Hale built the largest telescope. But we're going to focus just on the 100-inch telescope. So now you have the kind of telescope needed to make progress in cosmology. So now you need an astronomer. So where do you go? The University of Chicago. And Edwin Powell Hubble got his bachelor's degree here in 1910 and his PhD in 1917. And he came here not only as a scholar, but a scholar athlete. And there he is, a 6'3" power forward on the basketball team. And I bet most people in this room didn't know that the University of Chicago for 3 years in a row won the NCAA tournament. And well, it wasn't called the NCAA tournament then, but that's just a detail. And Hubble was the forward on 2 of those teams. And here's the Hubble Space Telescope. Now, some people, I've read, occasionally you read an article that says that Hubble designed this telescope, and he actually didn't. It was named after him. And you'll see some images from the Hubble Space Telescope. Here it is being deployed from the Space Shuttle. John Grunsfeld, who's a University of Chicago graduate, led the last 2 servicings of the Hubble Space Telescope. And John wanted to take something up of Hubble's. And so on one of the servicings, we sent up Hubble's thesis. And actually the front page of his thesis. And it's photographic investigations of faint nebulae. So he was really interested in the nebulae. His thesis was unmemorable, but it got him interested in it. And then the second time that John went up, and this took a lot of effort, and I'll tell this story at the reception, but not now. We sent a basketball. So this is to orient you, this is the space shuttle. Here out the window is the Hubble, and here's a basketball from that championship year. And getting NASA to send up a basketball was non-trivial. It's a very interesting story. And I was very excited. I received this image, this picture from John Grunsfeld by email from space. So that's still cool now. So what did Hubble do? So he figured out the architecture of the universe. He figured out that these nebulae, these faint nebulae, were actually other galaxies. And I'll show you how he did it quickly. But he determined the architecture of the universe, that it's made of hundreds of billions of galaxies. So he enlarged the known universe by a factor of 100 billion. That's pretty good. And here, Hubble is the one with the pipe. In all pictures where somebody has a pipe, it's Hubble. And here's the 100-inch. And so I've drawn galaxies here. And galaxies are about 100,000 light years across and millions of light years apart. And so how did he do this? This is the nearest galaxy, Andromeda. It's about 2 million light years away. And this is an image with a telescope before the hooker. So you can see that it looks like this faint cloud. Here's a Hubble image today. You can see it's a galaxy. And here is the aha, eureka moment photographic plate that he took. It's right there. So the hooker was powerful enough that he could see very bright stars in Andromeda, and he was looking for a certain kind of variable star. And here, at first, he thought it was a nova, and that's not what he was looking for. And then he realized that it was a variable star, so he crosses out N and puts VAR. And it's a variable star, and the variable star allowed you to figure out how far away it was. And what did I say here? It's far outside the Milky Way. So that was a really big deal. So I want to prove to you that there are 100 billion galaxies in the universe. So this is the Hubble Deep Field. It cost you $2 billion, and it was worth every penny of it. So Hubble pointed, and it's the Hubble point and shoot. It pointed at one direction in the sky for 2 weeks. And it's a tiny part of the sky, 1/30,000,000th of the sky. And if you don't believe me, there's only one star in this picture. That's what a tiny part of the sky is. There's the one star. All these fuzzy little things are galaxies. And last year when I taught in Paris, one of the labs was to have the students count the galaxies and then multiply by 30 million. And thank goodness we have a mathematician as president. So 30 million times 3,000 galaxies is 100 billion. And I'm going to go to the next slide very quickly because I'm not sure I got the math right. But so 100 billion galaxies. Before Hubble, we thought there was one, just the Milky Way. Of course, the other thing that he did was he put together the fact that the galaxies, that the universe is expanding. So let me just briefly tell you about that story. There was an astronomer named Slipher who measured the velocities of these nebulae. And what was striking about them and what got Hubble's attention was they move fast and away from us. So that's what got Hubble interested. And what Hubble did was to show there was a correlation between their speed, so speed is indicated by the arrow, and their distance. So the ones that are moving fast are farther away. And if you think about what that is, and think about running the clock backwards, that's basically the fingerprint of the Big Bang. So they all started here a long time ago, and then 13 billion years later, we're now seeing where they are. And of course, the ones that are moving faster will be farther away. And so he realized that, or he showed that the universe had a Big Bang beginning. And this found a ready interpretation within Einstein's theory of general relativity. This was not an explosion of galaxies into space, but an explosion of space with galaxies being carried along. So space is expanding, space is getting bigger, the galaxies are being carried along, and that's why they look like they're moving away from us. Okay. Hubble had one student, or I'm not even sure he was an official student, we might call him a protege, and that was Alan with 2 L's Sandage. And the second greatest astronomer of the last century. And in 1970, he characterized cosmology as the search for two numbers, and I'll tell you about those two numbers, H0 and Q0. And he wrote a very influential paper showing how the 200-inch telescope, which I showed you a picture of before, this is a beautiful line drawing, although it doesn't project so well, was going to solve everything. So let me just tell you what H0 and Q0. So this is what you learned on your mother's knee. There was a Big Bang. This is the size of the universe. And the universe is expanding. This is time. And because gravity is attractive, the lines are droopy. So the H0 is the speed which the universe is expanding today, and as time goes on, the speed slows down due to gravity. And the big question that Sandage was asking is there enough stuff in the universe for the universe to fall back on itself, or does it expand forever? And so H0, how fast is the universe expanding today? And by the way, 1 over H0 is the age of the universe, pretty important number. Q0 is how much droopiness, how much is the universe slowing down? So he said those were the two numbers. Not everyone at that time thought cosmology was a respectable field. So Lev Landau, the great Soviet physicist, said about cosmologists, often in error, never in doubt. Now, I'm not sure he said this, but I think he whispered under his breath, and always entertaining. So that changed with the discovery by Penzias and Wilson that we are immersed in microwaves. We're in a microwave oven. Thank goodness the temperature is pretty low. They discovered accidentally, this is a wonderful story, but I'll just tell you the upshot of it, that the universe is filled with microwaves. And these microwaves are the relic of the fact that when the universe began, it was extraordinarily hot. So it wasn't just a Big Bang, it was a hot Big Bang. And from that hot Big Bang, as the universe expanded, it cooled. And that completely changed the game. And now we're going to start getting to quarks and the cosmos here. Because when you heat something up, you reduce it to its most fundamental pieces. And we now know that the most fundamental bits are quarks. And so this is a full-size picture of all that we can see today just after the beginning. It was about this big, so the universe has expanded a lot, and it was just a soup of elementary particles. So let me talk about the 13.7 billion years, but I'll speed it up just a little bit. So we start as quark soup, and let me just walk you through this. As the universe expands, it cools, and as it cools, layer upon layer of structure is built up. So you start with quark soup. From the quarks, you make neutrons and protons, and I'll show you a slide of how you do that. And of course, everybody learned in school that neutrons are green and protons are blue. When the universe was a second old, it was a nuclear reactor. And some of the neutrons and protons combined to make helium. Some of them combined to make deuterium, a heavy form of water. Keep that thought in your head. A little bit of lithium and a small amount of helium-3. So I think that the strongest argument against intelligent design is the small amount of lithium that was made in the Big Bang. An intelligent designer would have realized we'd need a lot more lithium. But that's just my argument. As the universe cooled, so we first make the nuclei, and the nuclei of only the lightest elements were made in the Big Bang. The rest of the elements were made in stars later on. And when the universe was about 400,000 years old, atoms formed. And then gravity was the master builder. From that point forward, gravity took a slightly lumpy universe, and I'll tell you how it got slightly lumpy, and pulled matter together and made the galaxies that we see today. And this point, when the universe goes from being ionized, is the word we use, to being neutral, is an important point, because once the universe becomes neutral, photons in the universe can come straight to us. And so when we look at those microwave photons that Penzias and Wilson discovered, we're looking at the infant universe. I'll come back to that. So here are the quarks. So there are 6 types. So the first 4 are up, down, strange and charm, and then 2 more were discovered at Fermilab after these pictures were taken. Truth and beauty, top and bottom. And in fact, I noticed Mel Schockett in the audience, who led the team that discovered the top quark. And they come in 3 designer colors that have faded a little bit. And the particles that we know and love are made of 3 quarks. So a proton is made of 3 quarks, 2 ups and a down, and a neutron is made of 2 downs and an up, and they're held together by glue. Okay, so here is an important pause point. So this connection between quarks and the cosmos, is it trivial or is it profound? And trivial would be, it's a curious fact. And I'll give you an example of a trivial fact, that atoms are made out of quarks, and I'll talk about that next. But that doesn't really influence chemistry, and I'll talk about that next. So is it a curious fact? That's just the way the universe began, and of no consequence other than that. And that's what the cosmology establishment believed. Or are there profound connections? And this, for purposes of this lecture, I will call this the point of view of the Chicago School. And everyone can read this. Today everyone agrees that the connections are profound, and so that's where I'm headed. But let me just, again, so here is an atom, and chemistry is all about atoms, and an atom has a nucleus. Well, let's see, the protons are supposed to be blue and the neutrons are supposed to be green, but anyway, protons and neutrons in the nucleus. And then if you look at the inside a proton here, it's made of quarks. And so is there a profound connection between quarks and chemistry? And we got a bunch of chemists in the audience, and I think the answer is basically no. There's no, and that's because chemistry is all about this cloud of electrons. And so it doesn't matter what's going on in the nucleus. So here's water, and so these little puffy things are meant to be the cloud of electrons. And chemistry is all about what the electrons are doing. And the nucleus is so far away, it just doesn't matter. And so it's a curious fact that to build an atom, you start with quarks, but if you want to do chemistry, you don't need to know what a quark is. In fact, you don't even really need to know what a nucleus is. Okay, so this brings us to the Chicago School and the thought that there's a connection between inner space and outer space. And this is David Schramm again. And he went on a famous hike in the Dolomites with Leon Lederman, who was then director of Fermilab, and convinced Leon that, well, we ought to go to NASA and get some money to study whether or not there's a profound connection between quarks and the cosmos. And by the way, I'm making a long story short, get these two guys, Cobb and Turner, that's Cobb, that's Turner, and create this thing called the NASA Fermilab Astrophysics Center, and this will be the mother church of quarks and the cosmos. So that was in 1983. And so I spent that much of my career half-time here and half-time at Fermilab. And I want to bring in Stuart Rice because this again illustrates all things are possible at the University of Chicago. So Stuart was trying to solve a financial problem. And so he realized he could sell 50% of Michael Turner on the open market and help balance his books. So I hope you all saw this tongue-in-cheek. But I do have the purchase order to prove it. So for almost 20 years, a purchase order was put through the system every year. It says professional services. Well, you can decide after this talk if I give professional services or not, of Dr. Michael Turner, scientist in theoretical astrophysics. And we got it because we were the lowest bid. But I want to pause here because, again, so many people have helped make things possible. So here I am, I've just been promoted, and I go to Stuart and say, I want to spend 2 years at Fermilab starting an astrophysics group there. And then after those 2 years, actually I said 1 year, and then I came back and said, can I have another? And then I came back, it's like the asking a mouse for, the mouse who asked you for a cookie. And then I came back and said, can it be 50-50 for the next N years? And he said yes. If that's what it takes to do great science, the answer is yes. And so this period of 1980s I like to characterize as the go-go junk bond days of early universe cosmology. And so theorists like myself and Rocky Cobb, the hand wavers, we explored the consequences of the bold ideas about quarks, how the forces were unified, how the particles were unified, to see if the consequences of those ideas explain things in the universe. And we also sold t-shirts. So here's one of them, Cosmology Takes Guts. And this was a big seller. And on the internet now, you get a lot of money for that. We had the first conference on this subject at Fermilab. And in fact, in a couple pictures back, the picture of Leon and Rocky and I was at the banquet of this meeting, which was held in Hutch. And this conference was notable for two reasons. One, we convinced the University of Chicago Press to publish a conference proceedings. And we were told they never did that. And we said, but this one's going to be extremely important. This is going to be a milestone in science. And I don't know if it's a milestone, I think it's pretty important. And also, look at this. Michael Turner, co-chairman, Inner Space, Outer Space. That's what it was called. The official conference of the 1984 Summer Olympics. So in that picture with Leon, he was handing Rocky and I these plaques. And if you remember the 1984 Olympics, Peter Uberoff in Los Angeles, that was the first Olympics where they franchised everything, including the conference. Okay. Now we're really to the meat of the subject here. So what are those three really important ideas that you need to remember that are the profound connections between the very big and the very small? So first of all, the idea, and I'll explain this more, that when the universe was very young, it had an enormous growth spurt. That in a jiffy, that's a short amount of time, I won't use scientific notation, it grew by more than it has since. So a big growth spurt, and that if that growth spurt happened, it accounts for the fact that we live in a very regular universe, so we don't see all the galaxies in one direction. They're spread uniformly across the sky. It accounts for the heat of the Big Bang, says that the geometry of the universe is uncurved or flat, and explains where the seeds for galaxies come from. So that sounds pretty big. The idea that the dark matter that was discovered in the 1930s by Fritz Zwicky is not just faint stars, it's not dust, it's not something astrophysical, it's new forms of matter, elementary particles left over from the Big Bang. That's a pretty big idea. And then last but not least, the idea that there's a mysterious form of energy with repulsive gravity called dark energy. And it's causing the universe to speed up, not slow down. We'll come back to that. So first of all, inflation. So there was the following dilemma, that if you imagined all the possible ways the universe could start, and then asked what did the outcomes look like, an outcome that gave us a universe that looks like ours today was very rare, unusually rare, but possible. So you could just go away and say, whatever. Or you could say, you know, that's puzzling. I wonder if something happened in between the beginning and now that made the universe look the way it looks. That is, created the lumpiness that led to galaxies, made the universe smooth, and explained the heat. And so that's what inflation does. And inflation is a burst of expansion that blows up a tiny little bit of the universe, and I'm going to have the mathematicians help me. So here is a complicated manifold, real wrinkly, but there's a theorem in geometry that if you look at the tiniest little bit of it, it can be smooth. And so that tremendous expansion blows up that little smooth bit, which is in black, to be really, really big, and blows it up to such a great size that all that we can see today fits in there. And whatever it does that blows that up, the energy that blows that up gets converted into radiation, which is the heat of the Big Bang. And I'm really simplifying, but that's the basic idea. And here's the part that I played a little role in, which is very exciting. I'll show you an exciting picture in a second. So the idea was, could this work to make galaxies? We know at the smallest distances that the universe can't be smooth. Quantum mechanics, things are fluctuating, jumping around. So I've shown you a picture of quantum mechanical jumping around, fluctuations. But those are on scales, even if you don't know how big a galaxy is, you know a galaxy isn't smaller than a centimeter. Well, some theoretical physicists don't know that, but most people with common sense know that. And so this tremendous expansion due to inflation stretches these fluctuations on the teeniest scales and takes them to astrophysical scales. And these fluctuations become more and less matter. And so this blowing up of quantum fluctuations leads to the seeds for galaxies. And so the idea is, I'll show you what this picture is that noise, we call this is just quantum noise, gets blown up to astrophysical scales and seeds galaxies and larger structures. So the biggest things in the universe, is this a connection between, this is a profound connection, if it's true. And so the details of this got worked out at a wonderful conference that Stephen Hawking hosted in June 1983, the Nuffield Workshop. And can anyone recognize me? Yeah, I think you can. There's Alan Guth, the inventor of inflation, and Paul Steinhardt and I don't, and Bardeen worked out this idea of how the fluctuations, quantum fluctuations produce galaxy. And there's our host, Stephen Hawking. And I'm looking unhappy because we had a garden party before this, and Stephen's daughter Lucy was 13 at the time. And I went to Stephen and I asked for her hand in marriage. And he said, "The line is very long." Okay, dark matter. So Zwicky was studying clusters of galaxies in 1933, not at the University of Chicago, although given his personality, he would have fit in here very, very well. And so this is an inside joke for the astronomers. This is a beautiful cluster of galaxies called Coma. And what Zwicky noticed is that the galaxies are moving really fast. So all these little fuzzy points of light are moving really, really fast. So what keeps the galaxy together? Gravity, of course. And so he did a little calculation. Is the gravity of all the stars in all the galaxies enough to hold this cluster together? And the answer is no. It's off by almost a factor of 100. And so Zwicky discovered there's more to the universe than meets the eye. In fact, only about 0.5% of the universe is in stars. It's the dark side of the universe that's interesting. And so that started the question. So what Zwicky said is, oh, there must be some dark matter there. So he was being a detective. There must be some stuff that we can't see, maybe faint stars, maybe gas or whatever, that holds it together. And let me tell you where we are today. The idea that the Chicago School really pushed a lot was that the dark matter is a new form of matter left over from the quark soup. This today, by the way, is the most conservative hypothesis. Now, we all know that the most conservative hypothesis is not always correct, but this is the dominant view that most of the dark matter is a new form of matter left over from the Big Bang. David Schramm wrote a paper in 1980 championing the neutrinos, and he really liked the neutrinos. They're known as hot dark matter, and it turns out that neutrinos contribute about as much matter, we now know that, as do stars, but they're not most of the matter. And others of us at Chicago and elsewhere favored something called cold dark matter. And let me just talk about this particle, the neutralino. So cold dark matter are particles that are heavy and move slowly. Neutrinos are light and move fast. And so this is what everyone's focusing on now, is cold dark matter. And this is the lightest. This is a theoretical particle. It's not known to exist. This is a particle predicted by the particle physicists, not to explain dark matter, but to solve their own problems. And the number of them left over from the Big Bang, if you read the book that Rocky and I wrote, is about right to account for the dark matter. And so that's the idea. And then if you put these inflationary fluctuations together with cold dark matter and run it on the biggest computer, this is what happens. So this is, not a computer, but so here's the lumpy matter, and it gives you a very detailed story of how galaxies and structure form. So the first things that form are galaxies. The galaxies come together and form clusters, and the clusters come together and form superclusters. So it tells you, it's a very specific and predictive theory of how structure forms in the universe. So now I want to talk about another project. So you have that theory. How are you going to check it out? Well, we need to know the distribution of matter in the universe. And so Chicago got together with Princeton, Johns Hopkins, the University of Washington, and most importantly, Fermilab, to do a survey of the sky, the Sloan Digital Sky Survey, to actually figure out what the structure of the universe looks like. And the person who started that project was, the first director of it was Don York. And you'll notice this famous astronomer here, Jeffrey Stone, who was the provost at the time. And again, this is part of why Chicago's a great university. This project got into a lot of trouble. And if it were an airplane, it was heading at an angle like this, and it was about 100 feet above the ground. And this guy, our provost, was very tough with us, and he helped us write the project. And actually, both he and President Zimmer came to the dedication of this project that's been successful beyond what we told anyone. This was a University of Chicago graduate student, Connie Ricosi, who helped build the camera in this. This is what it showed us, and I don't have time to do this picture justice. So we're here. This is one direction along the sky, and this is a wedge of the universe. And each dot is a galaxy, and what you're supposed to see is that there are places that are relatively empty. Those are called the voids. There are places, there are linear structures that if you looked at them in 3D, they look like walls, and where the walls intersect, you see filaments. And this is precisely the kind of structure that this theory of cold dark matter predicts. And I'm going to skip that slide. And now we're on to dark energy. So in the 90s, this picture was starting to look really, really good, except we had a small problem that we didn't have enough stuff in the universe to make a flat universe. And so several of us said there must be something else out there called dark energy. And that, we'll get back to dark energy in a little bit. And that's the missing piece of the puzzle. And in 1998, two teams of astronomers discovered the most conspicuous effect of dark energy. It has repulsive gravity, and so the universe is actually speeding up rather than slowing down. So here's where we are today. This is cosmology circa 2000 or 2013. I underlined the word consensus. So, you know, not to gloat about the Chicago School, but let's just go through it and see what connections between quarks and the cosmos. So we talked about quark soup evolving to nuclei and atoms and galaxies and large-scale structure. We have a universe that inflation predicted that we should have the uncurved universe. We have just the right amount of stuff in the universe to make the universe uncurved. Looking over here, Einstein told us that the shape of the universe depended on how much stuff there's in it. If you have a high density universe, it curves back on itself like the surface of a balloon. If it's low density, it's curved like a saddle. And the Goldilocks universe, which is what inflation predicted, is uncurved, and that's what we have. The universe is made out of atoms. I'll give you the numbers. Exotic dark matter that still hasn't been identified, and mysterious dark energy. And all the measurements that have been made, and there are a lot of measurements that have been made, are consistent with this idea that the universe went through this inflationary growth spurt. And we also, there used to be, if you went to the dictionary under oxymoron, it said, for example, precision cosmology. And we now do precision cosmology. We learned about error bars. And so the amount of exotic dark matter is 22.7 plus or minus 1.4%. Atoms are 4.6 plus or minus 0.16%. Dark energy is about 73%. The Hubble constant, this famous, actually I don't have enough time to talk about this, but Hubble's famous constant, we've pinned down the age of the universe. Oops, I screwed up. This is a slide from 2 weeks ago, and I did not update it for those 2 weeks. We're not quite that good yet, but it's about 13.75 billion years, maybe a little bit more. And so this is where we are today. So let me just talk about a little bit of the evidence. So here we are, we look out in space, we look back in time. We're looking back to the time when the universe was about 400,000 years old, and it was going from ionized matter to atoms. And I told you that's where these microwave photons originate from. And these microwave photons, therefore, give us a picture of the universe when it was 400,000 years old, before galaxies, before stars, when it was really simple. And so here's the best baby picture we have. So the intensity of the microwave photons in different directions, so this is the whole sky. The intensity is color-coded. Where it's red, it's slightly more intense. Where it's blue, it's slightly less intense. And that intensity variation is really tiny, 0.001%. Does anybody know what 0.001% is? So that was the difference in votes that Gore and Bush got in Florida. And the other notable thing in this picture also does three things for you. Number one, if you're a cosmologist, this picture makes your heart go pitter-patter. If you're not, you know, it's whatever, it looks like noise. Actually, it is noise. It's that quantum noise I was talking about. And the last thing I want to point out is product placement. Do you see these two initials here, S.H.? Stephen Hawking. So the way we actually study this to learn about the universe is to do something called a multipole expansion. And let me just tell you very briefly what we do is that on this scale we measure the temperature difference between 2 points on the sky, and on this scale this is the separation of those 2 points. Small separations over here, because you remember the book of Genesis was written in Hebrew and this is an appendix to it, and so it goes from right to left. And so small differences, big differences in angle. And so there's a series of peaks. They're called acoustic peaks. The WMAP satellite mapped out a bunch of them. Steve Meyer was one of the handful of individuals who built that and made the measurements. And on the on small angular scales, it's mapped out by the South Pole Telescope, which is an instrument that John Carlstrom built. And this curve is the theory curve for the inflation plus cold dark matter. Fits pretty well, doesn't it? I can draw really good. I drew the curve through all the points. No, that's not true. So that's, let's see, I wanted to say one other thing about this. So this says, this feature you can actually see. This corresponds to a delta theta of 1 degree, and it says that there's a noticeably big temperature difference between 2 points separated by 1 degree. And I'll show you, you can see that with your eye. There we go. So the characteristic hot or cold spot on the sky, so like that blob or that blob or that blob, you can actually see it with your eye, is about 1 degree. The rest of the features, you have to do this multipole expansion. So one thing I just want to show is, why do we believe that the dark matter, so the Chicago School said the dark matter is not atoms, it's something else. And so I'm going to get just a tiny bit technical, but this is a really big deal. So the amount of deuterium made in the Big Bang, D, depends upon how much ordinary matter there is. We call it baryons, or B for baryons. The amount of deuterium made in the Big Bang was measured by someone who is a postdoctoral fellow at the University of Chicago. And so that pins down the amount of atoms in the universe. You can also measure the amount of atoms in the universe by looking at the height of the first peak to the third peak. And so you get a number. And you'll notice it's not 4%, but ignore that. So you get a number 0.021, because I have the Hubble constant in here. You can also, from the Sloan Digital Sky Survey and the height of the first peak, determine the total amount of matter. You get a big number, 0.13. Is there anyone in the room who thinks 0.02 is equal to 0.13? So this is the amount of atoms. This is the total amount of matter. They differ by 20 sigma. So that's our evidence that most of the matter in the universe is this exotic stuff. So we have this picture, this wonderful cosmology, and you'll have noticed that it's built upon these three pillars that involve quarks in the cosmos: dark matter, dark energy, and inflation. So what about these mysterious pillars? So people who've been listening closely will have noticed that we have yet to discover the dark matter. We don't know what the dark energy is. And could you tell me a little more about inflation? So we have this beautiful picture, the connections between quarks and the cosmos, but we don't know what these things are. And so that's where the future is. So in the year 2000, one of my supporters, who used to make jokes about, you know, quarks in the cosmos, but he was really a big supporter, was Bruce, decided to come to the dark side and decided to become a cosmologist. And he noticed that we had a lot going in cosmology at Chicago, but we weren't very organized. So he helped bring us together to form what's now the Kavli Institute for Cosmological Physics. And so I have pictures of people here. We have about 100 people at Chicago doing cosmology, if you count the students and the postdocs and the faculty faculty. So Bruce was the founding director and got us going. John Karlstrom was the second director. And as Bob Zimmer said, I'm the third director. So let me tell you what we're doing with these three things. So dark matter. We have the full court press on. So we're trying to make dark matter particles at the LHC. We're trying to detect them in our halo. And we're trying to detect the ones that hold together our galaxy. And we're trying to see them annihilate into other things that we can see. There we go. So there's Juan Kolar. And a few years ago, he got a signal. He built an ultra-sensitive detector, put it underground, and he's looking for the dark matter particles that hold together our galaxy. They're very shy. You have to build a very sensitive detector. He got a signal, and here was the article in Science magazine. Possible sighting of dark matter fires up search and tempers. It's hard to imagine Juan Kolar, it's not hard to imagine Juan Kolar as a matador. He's Spanish for one thing, and he certainly seems to relish waving a red flag in front of, you'll have to read the rest of the article. So one of his critics was an experiment called CDMS, and 2 days ago in Denver, CDMS published a paper. And previously they had said, you know, Kolar can't possibly be seeing anything. And if you read the bottom line here, it says, we now see something just like he saw. I'm translating it into English from the French. And it's not, we don't know that it's a dark matter detection, but the instruments are there, ready to make a discovery. And you all know about the Large Hadron Collider. We like to call it a dark matter factory. And of course, as you fly into Geneva, you see this giant red circle. And Mel, I apologize. They have beautiful detectors. And the detectors are wonderful. And they've made a wonderful discovery, the Higgs boson. Everybody knows about that. But I'm selling T-shirts that said, they built a $10 billion accelerator and all they discovered was the Higgs. And why is that? Because they know how to turn energy into new particles, and this is what we want. We want the dark matter particle. And so we could produce the dark matter particle at the LHC. And the other thing is our halo is filled with dark matter, and sometimes these dark matter particles bump into each other, and they transform their nature into things that are easier to see, like positrons. And so in the news the other day was an experiment led by Sam Ting on the space station that saw a positron signal very similar to one that Frank Wilczek and I predicted in 1990. So this is the number of positrons versus energy, and we predicted a rise and a fall. And so what did Sam see? Sam saw a rise, a leveling, and not telling anymore. So maybe there'll be a fall. If there's a fall, maybe we're seeing the dark matter particles annihilate. Let me quickly move on to dark energy. My colleagues accuse me, this is my favorite subject, they accuse me of wandering around the campus saying dark energy may be the most profound problem in all of science today. Well, I found out that great minds think alike. So if you go, since the time is short, I won't press this button, but in this interview, Katie Couric asks Sarah Palin about dark energy, and she says, you betcha, Katie, I believe in dark energy. We can see it from Alaska. And that's going to be your bumper sticker in 2016. So dark energy, I don't have time to do this justice. This is really weird stuff. This is stuff that has repulsive gravity. And it has repulsive gravity because it's very elastic. And if you're confused, you've caught up with us. And so we need to figure it out. And so Josh Freeman is leading a project that was started by John Peoples, the director of Fermilab, who got Fermilab into the Sloan, called the Dark Energy Survey. And Fermilab built a big, giant, half a gigapixel camera to put on this telescope in Chile. And Rich Krohn in our department is the deputy director. And John Karlstrom, again, that's John Karlstrom, at the South Pole. And his telescope can not only measure the microwave background, but it can study dark energy. And so finally, let me just mention inflation. So the smoking gun signature of inflation, what we're all looking for, is a kind of polarization imprint it leaves on the sky. So this is a hot spot on the microwave background, and this is the polarization vector of the light. And this is called E, and this is called B, and only gravity waves produced by inflation can make B. And if you find B, you will have found the gravity waves made by inflation, and they tell you when inflation takes place. This has become one of the holy grails of cosmology, or it may be a wild goose. And so John Karlstrom's smaller experiment, DAISY, discovered the polarization. It's a very, very tiny effect. And now they're outfitting that same old South Pole telescope with polarimeters. Okay, so I'm going to wrap up here. There are even more, this adventure is not over. There are bigger questions ahead. Some of you will have noticed that we started out with a really simple universe. We just had ordinary matter and galaxies, and now we have this recipe that's got atoms, it's got dark matter, it's got dark energy, it's got neutrinos, it's got this. Who ordered that? Can we make sense? And somebody can ask me about the multiverse. So one of the other predictions of inflation that we don't like to talk about a lot is the idea of the multiverse. What happened before the Big Bang? That is now a question that's within the realm of science. We don't know the answer. This connection between quarks and the cosmos, we hope that by studying the origin of the universe, we can complete Democritus's quest of finding the fundamental building blocks and the rules they obey, and even ask the question, what is the origin of space-time and the laws of physics? So here's another way of looking at this. This is a view graph that my daughter helped me draw. I said, Rachel, we know a lot, but we understand less. Can you help me put this all together? So here are a bunch of the pieces I talked about. And I asked her, Rachel, because the challenge is putting it together. And it's going to be the young people, not the old people, who do that. I asked her, can you put that together? And she said, Daddy, you have an elephant. And so in cosmology, we're like the 6 blind men in the Indian tale feeling an elephant. And, I forgot about big telescopes. So I was talking about big ideas, and Chicago is back in big telescopes. So we are a partner in the Giant Magellan Telescope that will be in the mountains of Chile. And guess what kind of telescope it is? Reflecting mirrors. So I hope I've convinced you that there are deep connections between quarks and the cosmos. And today, the mysteries of cosmology are also the mysteries of particle physics, and that the very big and the very small are inextricably, that's such a great word, linked. And it all started here at Chicago. This is a view graph that Dave Schramm made, and even prettier than mine. The study of the very large cosmology and the very small is coming together. I think he got it right. And I just want to end with this. Oh no, how did that happen? At Chicago, ideas really matter. Ideas matter. We shape the way that people look at the universe. Thank you very much. Take a few questions.
Michael, can I ask a question?
Do you have the microphone? You have to have the microphone.
I have the microphone.
Okay, good.
Michael,
you can ask a question.
Michael, Jerome Frizzell, class of 1983, University of Chicago. I was the first class you taught in astrophysics in '81. You gave me a C. That's why I became a lawyer.
That's a good grade.
That's why I became a lawyer.
That's a good grade.
Michael, quickly, with respect to the Higgs boson, and just for us folks that aren't tracking it, can you just briefly give us the sense of what the import of the discovery of Higgs was in respect to the theoretical model?
So the Higgs boson, oops, I didn't mean to do that. The Higgs boson completed what's called the standard model of particle physics. So this is the model that explains virtually everything we know on Earth. And, and the Higgs explains why particles have mass. But this model points to questions that aren't answered. So why are there quark-like particles and lepton-like particles, like the electron and the neutrinos? Why are there two separate sets of particles? Why are there three forces? Why aren't they unified? So that's the thing that we're really looking for at the LHC, are clues to the grander theory. So this theory that they call the Standard Model that explains virtually everything here on Earth, but it doesn't explain dark matter and dark energy, is more or less complete. So the other thing that got cosmologists excited about is with inflation, this whole idea of inflation, which I painted with a very broad brush, is based upon a cousin of the Higgs. So we now know the Higgs exists, and particles always have cousins. And so we're very excited that we might eventually discover that cousin and have the explanation for inflation. Jim, you're supposed to wait for the microphone, even though you have a big voice.
I'm embarrassed to say this, but I think you missed one very important thing. Why are we a matter-dominated universe?
You should not be embarrassed to say that. So Jim said, why is there only matter and not equal amounts of matter and antimatter? And I have to tell you that that's why Jim was interested in coming to talk to me, because the very first puzzle I worked on is the mystery of why there's no antimatter in the universe. And that is another, I had to make choices in fitting this into 2 hours. And the fact that there's no antimatter and that we just have matter is a very deep puzzle. And before we started talking about the connections between quarks and the cosmos, we had no idea. We now think it's connected to the discovery that you shared the Nobel Prize for, the fact that the laws of physics slightly, and I'm going to paint with a broad brush here, favor matter over antimatter. They're actually just different. And so that's a puzzle that got us going in this Quarks to the Cosmos, but we haven't made much progress on, and so I didn't mention it here. But that's the most profound puzzle, which is, where did the atoms come from? I think Steve Berry has a question.
This will be our last question.
You've given us a very nice picture of the history of formation of ordinary matter. Do we know anything about when and how dark matter could have formed?
So the dark matter came out of the quark soup. And let me tell you, and that story is very, very brief. So the quark soup, early on, it was hot. All the particles that nature created were there in great abundance. As the universe cooled down, the heavier particles could no longer be made, but they could find their antiparticles and annihilate. But if you had a particle that was very shy, like the dark matter particles are, eventually they couldn't find their mates to annihilate, and so some of them are left over. And so this was a calculation that was done in the early 80s, and particles like the neutralino and have just the right interactions so that the right amount of them are left over. So we take that as a clue, and it may be misdirection or it may be a clue. So thank you very much.